which is going to be introducing you to the Laplace, okay, and Poisson equations, okay? So we've wrapped up Sturm-Liouville theory for now. You'll have some practice problems on that on your current homework set, okay? We were able to apply it to wave solutions, okay? So let's kind of frame the Laplace and the Poisson equation a bit, okay? Remember that the wave and the heat equation, which are the main PDEs that we've been looking at so far, they're initial value problems, could be initial boundary value problems that tend to evolve in time, okay? And these are hyperbolic and parabolic PDEs, right? They're the canonical hyperbolic and parabolic PDEs, okay? Now, we're going to consider, okay, time independent, okay, boundary value problems, right? So, and in particular, we often consider these on bounded domains, although we're gonna start with some analysis on unbounded domains. Okay, so this brings us to elliptic problems, okay? And to start with, we have Laplace's equation. What's Laplace's equation? Well, it's given by the Laplacian, probably not surprisingly, acting on u is equal to 0, okay? For x lives in capital U, which is just some open subset of Rn, okay? Would look a little something like this. It has a boundary. It has a normal sticking out of it. So you might think, oh, we're going to come across some Green's identities, okay? And so this is our, values of x inside of U. The closure would include the boundary, right? But the interior is U, right? Now, what kind of boundary conditions could you have, right? Well, one might be Dirichlet, right? On the function itself, u of y is equal to f of y. Okay, that's what gives a flavor to your solution, right? Otherwise, your solution is going to be boring if you just have homogeneous boundary conditions, right? And Neumann are going to be conditions on the normal derivative to the boundary. It's equal to some function g defined on the boundary, okay? So this is our derivative normal to the boundary, okay? Great. So this is Laplace's equation. We'll talk in a bit sort of where this comes from, right? Or a couple of different examples, okay? Functions u of x that satisfy Laplace's equation, okay, are called harmonic. Harmonic functions have special properties, right? Where does this equation come from? Okay, there's actually many applications of it, right? Image processing, there's a lot of areas of mathematical physics. Let's talk about two, okay? First of these is the steady state solution to the heat equation. steady state heat conduction, right? So let's say maybe we have a heat equation that evolves on, some subset of Rn. And it's got some initial condition, G on U, and it's got some, let me write this down here. It's got some boundary condition. Okay, so this is our IC here, and our boundary condition. Okay, this could be like the temp at the boundary. Maybe you have some shape, you're heating a potato or something like that in the oven. The oven gives you the temperature of the potato on the outside here, and it's seeping in, right? And so you have f of y here. This is x in u, and drawing it here, right? Essentially, the boundary condition diffuses into u, right? So that's what happens with diffusions. Then diffusion, things diffuse, right? Okay, so this is on our boundary here, du, okay? And with diffusion, essentially what we expect is that in the limit, as time goes to infinity, u of xt is equal to v of x. Well, eventually, right, you're no longer going to have changes in time, right? You're going to reach some steady state. Well, this steady state solution satisfies that the Laplacian of v equals 0, right? Because you have no time dependence anymore. And that v of y is equal to f of y, okay? So, steady state solution to a heat equation. That's one way to get Laplace's equation. Second example, electrostatics. Okay, so let's say that something I'll call E of x, which is itself a vector function. Let's say this is an electric field, okay, induced in some way, and that B of x is a magnetic field, okay? Gauss's law, I don't know if I've apostrophized that correctly. Gauss's law says that the divergence of E is equal to 0, okay? For this electric field. Faraday's law says that the curl of E is equal to the time derivative of B, which is equal to 0, right? Because B is not changing in time, right? So on X and U, because we're here in the static case, okay? Well, if we set, okay, E to be the gradient of some U, right? This you could think of as like a scalar electrostatic potential, okay? Then Gauss's law, it implies that the divergence of the gradient of U, right, which just gives us the Laplacian of U is equal to 0 on X is in U. Okay. So we get back Laplace's equation. How do we get back the boundary conditions? Well, if we prescribe, okay, electric potential, okay, or voltage, okay, on the boundary, then U of y is equal to some electric potential. Let's call it rho of y on the boundary. Okay. On the other hand, we could prescribe some surface charge, okay, or electric field on the boundary, okay. In that case, it would be the unit normal dotted with the gradient of u, y, is equal to something called sigma of y, okay. We'd also call this dN is equal to sigma of y, okay. This up here, right, is a Dirichlet boundary condition, and this down here is like a Neumann boundary condition, right? Where this here is like our unit normal along du. Okay, so that's two different ways Laplace's equation will come about, right? We could essentially be solving for the electric potential inside of some volume or some material that we're inducing electricity into. It could be a metal plate that we're heating, maybe even non-uniformly along the exterior. Lots of different things, right? So that's where this comes from, okay? Now, the next thing we'd maybe like to do is understand what the solutions to Laplace's equation behave like. And just like in the case of the heat equation, we derive the fundamental solution. We're going to do that again here in the case of Laplace's equation, okay? And so in order to get there, we'll start with a homogeneous